All right. Good morning, everyone. Today we will finish chapter one of this workbook, which is introduction. Yeah. And from the next lecture, we'll do some calculations. That's also going to be revision of our previous course, which is statics. And then from there, we're going to move forward. So today also, it's going to be like pretty basic stuff and revision of statics. So last time we talked about motivation and some branches of physics and mechanics. And today we're going to talk about some general principles of statics, which is also going to be like revision. And then we'll talk about units of measurements. We're going to talk about loading types. So loading type is important and the sign conventions are important, but the rest I think is basically revision of what you guys have studied in the previous course. In the last lecture, we talked about the motivation that why we need to study mechanics of material because it teaches you how things fail. So, if you want to understand what happens to the material when loads are being applied, so that's the subject which is gonna teach you about these things. And it is an extension of the previous course, which is statics. So what you're going to do is that you're going to add some additional concepts onto the subject which you've already studied in the last semester or previous semesters, and you're going to add deformation, and then you're going to also understand how materials or bodies fail. We talked about some principles of mechanics, like everything that happens in this world happens, it follows some kind of laws, and that laws are basically defined by principles of mechanics. So we also discussed about the application of this subject. So it's used in basically all kind of disciplines, and it is used to analyze different things, for example, buildings or machines or any kind of like object. And we can use this subject knowledge to basically analyze any kind of structure and also design and optimize these buildings. We also talked about branches of mechanics, and we also talked about history, where it comes from. So you have like ancient scientists from antiquity to 16th century, and then you have what we call scientific revolution, and that is from the 16th century to the 19th century, and that gives us classical mechanics. And this is what we're going to be talking about in this course. So you have some of the famous scientists, Newton being the most famous in this field, and he proposes three laws of motion and laws of gravity, and we're gonna roughly discuss what these laws are and what is gravity. And then it is also important that the field is still growing. It's still like, so you have like newer branches emerging. So for example, in the 20th century, you have different fields. For example, you have quantum mechanics, you have relativity, you have chaos theory and stuff. And people are also trying to combine all these kind of theories to a unified theory, which will explain all laws, no matter what type of body is, either it's very small or very big or normal. So, so we had classical mechanics and we have relativistic mechanics and quantum mechanics. But what we will be doing is that we will be focusing on this classical mechanics, which is basically like we'll be following Newton, what Newton has said. So we also talked about the branches of mechanics. So there are three main branches of mechanics. You have rigid body mechanics, you have deformable body mechanics, and then you have fluid mechanics. So in fluid mechanics, the body is fluid or a gas. So this is outside the scope of this course. So you have rigid body mechanics, and then you have deformable body mechanics. In rigid body mechanics, the assumption is that the body is rigid. It means that it's not going to deform or change in shape when the forces are being applied to that body. So that's what you guys were studying in statics. So in statics, statics is basically effect of forces on bodies, but the bodies are rigid, so they don't change shape, and also they are at rest. In dynamics, you remove one of the assumption and the bodies are moving, and then you figure out what are the forces in that body. So deformable body mechanics is an extension to statics. So in statics, you had assumption. We're going to remove that assumption, and then we're going to see if forces are applied, how the body deforms, what's going on inside the body. So we'll calculate stresses, strains, deformations, and we're going to see how it fails, how much load it can take. So that's going to be in the mechanics of materials. So to simplify, mechanics is statics, and we also learn some newer concepts about stresses, which, so you have statics. Because of the statics, you can calculate internal loads, you can calculate uh, reaction to the forces, and then because of those internal loads, you're going to have additional things, and those additional things are stresses and the deformations. And because of these stresses and deformations, you're going to see failure. So that's what we are interested in. We are interested in calculating what's going on inside uh, the body. For example, if we talk about simply supported beam, we are interested in what are the internal loads in the simply supported beam, and because of those internal loads, what are the stresses and what are the deformations, and how much stresses that simply supported beam can take uh, without failure. So this is the bookish definition. It's written in the book. So mechanics of material, some people call it strength of material, is a continuation of statics, where materials are allowed to bend, deform, and yield. So we're gonna review some statics concepts. That's gonna be like, so this chapter is also gonna be like basic stuff. And in the next lecture, we'll do some calculations. That's also gonna be review of statics. And from the next week, we're gonna start working on chapter 2, which is about stresses and strains and stuff. So I want to talk about 4 things as a review of statics. So one is basic quantities, another one is realization, and then you have laws of motion, which is proposed by Newton, and the law of gravity, that's also proposed by Newton. So I want to talk about 4 basic quantities. So there are other quantities as well, but these are the quantities which are going to be the most important for this subject. So these are the 4 basic quantities, which intuitively you guys all know what length is, what time is, what mass is, and what force is. But by definition, length is actually straight line distance between 2 points along an object. So if you have 2 points, you draw a straight line between these 2 points. So the distance of that straight line is called length, but you guys all know what length is. So, and then, I mean, what is time? Time also intuitively we know what time is. So, but by definition, it's an interval between succession of events. So in this world, like events happen simultaneously, and you have succession of events. Something happens, and then something happens, and then something happens. So interval between something happening is called uh, time. So that's the definition. But you guys know what time is. And what is mass? Mass is basically measure of a body or amount of matter in a body. So that's mass. So mass is measured in kilograms, and that kilogram is a unit, and we're going to talk about those units as well. What is a force? So force is, to simplify, force is just a pull or a push in a particular direction. So that's what we call force. And idealization, by definition, is simplification of some theory. So we need idealization because we cannot model the entire thing as it is. For example, if this is a table and we want to calculate the reactions of the table, it's not important to figure out everything. For example, it has little tires as well, and it has like so many things, but we can simplify this, and then by simplifying it, we can solve our problem. So simplifying something, some real thing, is called idealization. So when you guys were doing free body diagrams for your examples, for example, simply supported beam, so that drawing free body diagram is basically kind of doing idealization of an actual thing. So there are different types of idealizations. So I'm going to talk about 4 types. So you have particle, which is the very basic kind of an idealization you can do on an object. So for example, you can define a table by a point as well, for particle as well. So what is particle? Particle is something that has mass, but you have ignored the size because maybe the example you're doing, size is not important. So maybe you have ignored that and you just like are interested in what the mass is. So you can idealize that object as a particle. So you can also idealize like table, for example, as a particle as well. And then you have a rigid body. So by definition, I know I was talking about rigid body a lot, but by definition, rigid body, it's so a body is a combination of particles. We know what particle is. A particle has mass, but the size can be neglected. So if you have bunch of different particles, so the combination of particles and the particles remain at a fixed distance between them as well. They don't change the distance. So particles have fixed distances. When force is applied, the distances are going to remain fixed. So saying this is that it's not going to change shape. So if something is not going to change shape, that's a rigid body. And then forces basically are represented as this. So concentrated force, this is an arrow. So for example, you have a house, you have a roof, and on the top of the roof, you have a lot of snow. So you cannot just show, when you're doing calculation, you cannot show snow. Instead of snow, you can just point an arrow, and that would indicate that snow is applying a force. So instead of modeling entire snow, you can just like use concentrated force idealization, and that will show another person, or if you're doing calculation, that will show you that this is something force is being applied onto some object. And deformable body is similar to rigid body, but in the deformable body you have different particles, and those particles can change they're not at fixed distances, so you can change shape basically. So these are four kind of idealization you can do. There are many kinds, but that's the like you just the point of explaining this is that you have a real object and you want to do the calculations, you want to calculate reactions, you want to calculate the internal forces. So you cannot like model the entire thing. So you need to do the simplifications, you need to do the modeling or the idealization. So that's what idealization is. And let's just go through laws of motion. So there are three laws of motion which Newton has proposed. The first law says that an object at rest remains at rest, and an object in motion remains in motion at a constant velocity. So basically, like the object which is at rest is going to stay at rest. An object which is moving with a constant velocity is going to keep on moving with a constant velocity. So that's the first law. And second law says that if force is being applied on that stationary object, it's going to start accelerating. So that's the second law. Second law says force produces acceleration. And by the way, this figure which I have drawn, this is also an idealization of a real thing. So maybe that's a car moving. So we are not interested in the size of a car, but we are interested what mass of the car is. So instead of like drawing the entire car, I have just drawn a circle. That's an idealization in terms of particle. So this is an idealization. You have mass. This is also an idealization that something is being pushed. I mean, there's a force on a mass. So so second law says that force produces acceleration. So F is equal to ma. And then you have third law of Newton. So Newton said that for every action, there's an equal and opposite reaction. And the mutual forces, action and reaction between two bodies are equal, opposite, and collinear. So basically, if something is in equilibrium and you have forces being applied, so the forces should be equal but opposite in direction. That's why something is in equilibrium. So we use this third law, basically equilibrium equations, which you guys used to solve all sort of beams and columns or trusses. We use Newton's third law because it says like so the summation of all forces would be equal to zero. So force A plus force B should be equal to zero if the system is in equilibrium. So that's where equilibrium equations are coming from. And then you have a law of gravity. So, I mean, Newton says there is a force which is acting on the bodies, and that's the law of gravity. So it says any particle of a matter in this universe attract any other force varying directly to the product of masses and inversely as a square of distance between them. So that's the equation which Newton gave, and the so that's also an idealization of two bodies. Let's just say this is sun. Let's just say this is Earth, and so I've just drawn one circle. This is idealization to do the modeling. The distance between them is r, which is radius, and that's how you can calculate the weight of anything. So that's like four things, which is the foundation for statics, and it is also the foundation for mechanics of materials. So units are important because it gives a meaning to the physical quantity. So for example, if I put this number 15, you know what 15 is, but you need something, that something is called unit, to figure out what 15, I mean, for example, 15 second or 15, kilometer, or 15 Newton if it's force. So you need something with that numerical value to know what that thing is like. So that's the thing which you are putting with the numeric value is called unit. So by definition, unit is used to measure a physical quantity such as mass and length, which we talked about. So there are two systems of units. And by the way, I mean, you guys all know this already, but I'm just like revising this. And so there are two units. You have system international, and then you have US customary. So basically, you have one system that the whole world follows, and then you have like US system. So system international is international system of units, and US customary is United States customary system of units. So the system international units for the length, time, mass, force are, so for length, in system internationals, we use meter. And for the time, we use second. And for the mass, we use kg. And for the force, we use Newton. So the letter, we're gonna, when we use m with some numeric value, it would mean meter. And then you have time, mass, and force. For the US customary, you have these units. So if we want to define length in US customary, we'll use feet or foot. And for the time, it's same, but for the mass, it's slug, but that's a combination of different units. And for the force, pounds. So if we are talking about force in pounds, that's US customary units. But if we talk about force in Newton, that's we're talking about in system international. And there's another thing which is called prefix that goes with the unit. And prefix, what prefix is, it is a specifier or a mnemonic. I mean, that's added to the units. And what it does is that it indicates multiples or fractions of unit. So what I mean by that is, like, for example, if you are measuring some reading, and if someone asks you what's the reading, so instead of saying my reading comes out to be 0.00000000001 meter, I mean, it's better to say my reading came out to be 1 nanometer. So this nano word, this n which we use, that's a prefix. So this meter is a unit, and this nano, what we used, is a prefix. So prefix is basically used to indicate multiples or fractions of units. So for example, you have this much amount of something, so maybe you have this much Newton force being applied to some object. So instead of writing 1,000,000,000,000 Newton, I mean, it's preferable to write 1 giga Newton. So this Newton is a unit, but this giga is a prefix. So I mean, that's how you write stuff with the numeric values to explain what these things are. So there are some rules to this, but I think that's the most important one. So the quantities basically are separated by a dot. So for example, you have two quantities. You have meter, which is length, and you have second, which is time. So you have something, some value, which is defined in terms of meter and in terms of second. So this, you would put dot in between so that the reader can know that you're talking both of the things are actually quantities. But if you would not put a dot, so it would indicate that this is maybe a prefix. So that's like people try to separate the prefix and units, but some people follow, some people don't follow. So you have other rules as well, uh, so that we can know is it a prefix or is it a unit. But for you guys, it's important to understand like you have a numeric value, you have a unit, and you also have a prefix, and that would basically define a quantity. So this loading type is important because we need to know what loading types we are talking about so that we can figure out the stresses and strains and stuff. So there are three types of loading. I would call them loading types. And you already know this from statics, but we're going to just review it one more time. So the first type of loading is called external loads. So what is an external load? So external load are loads which are being applied onto uh, an object or a body. So for example, in this example, we are talking about simply supported beam. So simply supported beam is also an idealization of an actual beam. So simply supported beam is a beam that has pin joint at one end and a roller joint at another end. So that's a simply supported beam. So this is a simply supported beam, and external loads are loads which are being applied on top of that simply supported beam. So that's the external load. So for example, if you have a building, you have a roof, you have snow, the snow applied force onto the roof. That force is called an external force. So I've highlighted all these external forces in red. So there are four kind of external forces. So you have a point load, you have a distributed load, you have a moment, and you have a torque. So this 300 Newton force, that's a point load. So that's like at one point, there's a force being applied, and this type of force is called point load. So 300 Newton force, which is being applied onto that simply supported beam, is point load. And then you have a distributed load. So distributed load is basically a bunch of point loads being distributed throughout on a length. So that's a distributed load. And distributed load is defined in terms of Newton per meter or pound per feet if you're talking about US customary. So these units are system international. So that's the distributed load, which is distributed along some length. So that's like Newton per meter. And then there's another type of load, which is moment, and moment is Newton meter. So in this example, 20 Newton meter is a moment, and moment is a load that causes bending. So, and there's another which is torque. So torque is a kind of moment, a kind of load that causes rotation. So in this example, 10 Newton meter is torque, which is being applied onto that simply supported beam. So all these kind of loads are external loads. So they are being applied externally onto that simply supported beam. But what will happen as a result? So what will happen is that you're going to have reaction load because, Newton's third law, it says action and reaction are equal and opposite. So we know that this simply supported beam is at equilibrium. It's not moving. So you need to have those reaction loads for this beam to stay in equilibrium or at rest. So these are the reaction loads. And the thing is that reaction loads are always you're going to see the reaction loads at the supports, or you call it like constraints or boundary condition. So for a two-dimensional problem, and I've highlighted these loads as blue. So external loads I've highlighted as red, reaction loads I have highlighted as blue. So reaction loads will be as a reaction to the external load. So there are three kind of reaction loads for a two-dimensional problem. You have horizontal load, which is in this direction, horizontal direction. And then you have vertical load, which is along the vertical direction or y-axis, if this is x-axis and this is y-axis. And then you have a moment, which is which will resist bending. And the important thing is that you can calculate these reaction loads as the supports, which can be called constraints or which can be called boundary conditions. So in statics, maybe you have learned this, that there are basically some other boundary conditions as well, but these are the most important ones. So you have a roller joint. Whenever you see a roller joint, you can like know which kind of reaction forces you can expect. And then you have a pin joint, and then you have a fixed joint. So in pin joint, you will always have one reaction load. That's the vertical one. That's the one you're gonna have. For the pin joint, you're gonna have two type of reaction loads. You're gonna have vertical one, and then you're gonna have the horizontal one. And for the fixed joint, because fixed joint can resist bending as well. So you're gonna have three kinds of reaction load. You're gonna have horizontal reaction load, you're gonna have vertical reaction load, and then you're gonna have the bending reaction load as well. So it's gonna resist forces from both the directions, and it's also going to resist the bending. So how you can calculate these reactions? So external loads are clear. We already know what are the external forces, so we know the external loads. But we need to calculate the reactions to those external loads. So how you can calculate is that you can calculate by using Newton third law or equations of motions. We call them equations of motions or equilibrium equations. So for a three-dimensional problem, for two dimension, you can basically do summation. So if you do summation of forces along x-axis is equal to 0, you're going to calculate horizontal forces. If you're going to do summation of forces along y-axis, you're going to calculate some of the vertical forces. And also you can do summation of moments at any point equal to 0 to calculate. So you have three unknowns for a two-dimensional problem, and you have um, three equations for two-dimensional problem, equilibrium equations, and you can use those equations to calculate the reactions. And I guess you were using this to do statics a lot. So what's next? So there is another set of loads which are called internal loads. So in internal loads, so this is external loads, and then you have reactions. So now you know what's going on outside the simply supported beam. But what we are interested more is what's happening inside the simply supported beam. So because that's the one which is more important. So in order to expose internal loads, you cut a section. I think have you done a method of sections in trusses? Yeah. So what you do, if whenever you have to expose the internal loads, you cut a section, and then when you cut a section, you're going to expose additional set of loads, and these loads are called internal loads. And I've highlighted these internal loads in black. There are, for a two-dimensional problem, there are three types of internal loads. You have axial force, which I guess you were calculating in trusses. So in trusses, when you were doing method of section, you were cutting a section, and the forces which were being exposed were axial forces. So you have three type of internal loads. You have an axial force, which is represented by F in this case, which is a horizontal load. But basically, if you have a simply supported beam, so that's the longitudinal axis, right? So along the line, that's called longitudinal axis. And the force which is acting along that longitudinal axis is called axial force. And the force perpendicular, which is perpendicular to the longitudinal axis is called shear force. Have you heard shear force before? Okay. So that's the shear force. And there's another load which is called moment. So you have, whenever you cut a section, you're going to expose three kind of internal loads. You will expose axial force, you're going to expose shear force, and you're going to expose internal moment. So that's how it's going to be. The first step is going to be like, what are the external loads? And then the second step is going to be, you will calculate reaction loads by figuring out what are the constraints and boundary conditions. And by using the equilibrium equations, you can calculate the reaction loads. And then the next step would be, you're going to expose the internal forces, and then you're going to figure out what are the internal forces in the thing which we are discussing, for example, in this case, simply supported beam. So you have axial force, you have shear force, you have internal moment. There's another thing, torque, which causes twisting. Have you heard about torque before? So the torque is basically similar to moment, but it's on another direction. So moment causes bending, but torsion causes twisting. So just in case, if you have an external torque, you're going to have, if it's a fixed support, you're going to have reaction to the torque, and you can expose the internal torque by cutting a section. So that's the standard practice. You're going to draw a free body diagram, you're going to see what external loads are, then you're going to calculate the reactions, and after calculating the reaction, you're going to cut a section, you're going to expose internal loads, and you're going to use equilibrium equations and a couple of other things to calculate the internal loads. So these are the three things which are important, and that's the standard practice in this course. We're going to be using this a lot. Okay, so now we know the loads. We know the external loads, we know the reaction loads, we know the internal loads. So the interesting thing is that these internal loads especially, they produces stresses and they produces strains. And this is what is super important for us. I mean, we need to know the stresses and strains inside the simply supported beam or truss or any other body. And these stresses and strains can cause failure. So remember, I mean, we were interested to calculate the failure. We are interested to know when something will fail. So in order to know when something is going to fail, we need to know stresses and strains inside that thing. For example, if we are interested to know when the ship will fail, we need to know that if it's going to hit by an iceberg, what are the external loads which are being applied on that ship as a result of that impact, and what are the internal loads. And because of those internal loads, we need to then calculate stresses and strains. And once we have stresses and strains, we can calculate failure, because every material has a limit. Every material can only take stresses and strains to a limit. So if there are more stresses being applied to that material or object or a body, it will fail. So that's important. External loads, then you have internal loads, and the reaction. From the internal loads, you're going to calculate stresses and strains, and from the stresses and strains, we're going to see if it failed or if it not. So that's the overall process. So in chapter 2, we're going to talk about stresses and strains basically. Well, in this chapter, we're going to talk about loads, but in the next chapter, we're going to talk about stresses and strains. So from the internal loads, we're going to calculate stresses and strains. So that's how, so we know what axial force is, right? So axial force produces different kind of stresses. It produces normal stress and normal strain. That's going to be chapter 3 of this workbook. We also have torsion, internal torsion. So whenever you have internal torsion, that will produce shear stresses and shear strains. And we'll talk about that in chapter 4. So chapter 4 is about internal torsion basically. And when you have shear force, that produces shear stresses. If you have bending moment, that also produces stresses, but these are different type of stresses. These are axial stresses. And I mean, when we'll review those chapters, it's going to be like easy for you guys. But right now, I'm just like giving you overview that what kind of stresses you can expect. And we're going to talk about shear force and bending moment and the stresses causing because of those shear force and bending moment in chapter 6. And chapter 5 is going to be like drawing shear force and bending moment diagram. So you can know like what are the stresses along the length. For example, in simply supported beam, if you draw a shear force and bending moment diagram, you can know which point has what type of shear force and what type of bending moment. So you can select that specific point to calculate the stresses and to calculate the failure. And I mean, so far we'll talk about the stresses, but these forces, as we know now, we are beyond the rigid body assumption. So the forces will not just create stresses, it will also change the shape. So changing shape would mean like it will cause deformation, it will cause bending. So I don't know in statics if you have done this, but if you have a simply supported beam, you have a bunch of loads, you're going to calculate the reactions to that loads, and then you're going to expose, and you'll also have internal forces. But you will also have one another thing. So if you have a bunch of loads, because of those loads, it's gonna bend. Like the beam is gonna bend. So I don't know if you guys have done like, so yeah, that's another thing. Like in statics, you were just calculating reactions, but actually what happens is like the beam bends as well. So you have changes in shapes as well, and we don't want beams to bend a lot, you know. So that these things we will see in chapter 7. So whenever the force is being applied, you will also have change in shape. So we will study the changing in shape and how we can calculate how much change of shape we can observe under a certain amount of loads. We're going to talk about that in bending angle and deformation in beams in chapter 7. Chapter 8 is about special topic pressure vessels. We're going to talk about that. And then, I mean, in a beam or in an object, you don't have one single force. You have combined forces. So you have a bunch of different external loads. You have a bunch of different reactions and different type of internal forces, and you that will produce all sort of stresses and strains and could trigger a complicated type of a failure. So you have like so many different type of external loads, many type of internal loads, so many reaction loads. So you have all sorts of stresses. You have normal stresses, shear stresses, bending stresses. So you have some of bunch of different stresses like acting all together. That's what we're going to talk about in combined loading. So what happens when everything is like there are more than one forces acting on a body. And so because of that, you have like newer concepts. So you need to know about like Mohr circle, stress transformation to figure out these things. And the chapter 11 is going to be about the failure, like how things fail. So that's going to be this subject. So before we will next time we'll jump to the calculations, and but those calculations will also going to be revision of statics. So we'll try to calculate the reaction loads using the equilibrium equations. And from the next chapter, we'll go to the stresses and strains in chapter 2. But before, this is the last topic, which is about sign conventions, because when you guys were doing calculations, you guys need to know which force is positive, which force is negative, which moment is positive and negative. So to do the calculation, you need to know. So the most accurate way of calculating the sign convention is right hand rule. But we're not going to be using right hand rule a lot. We're going to be using conventional things which we were using in statics. But it's important for you guys to know that if you cannot find the direction of the coordinates, or if you cannot find what is the direction of the force, is it positive, is it negative, is it moment positive, negative. So the best way to figure this out is by using right hand rule. So we're going to talk about right hand rule. So what right hand rule can do is it can give you two things. It can also give you the direction of the coordinate system, and it can also provide you the signs for the moments. But in I think statics, the counterclockwise moment was positive and the clockwise moment was negative, right? That's what was the assumption. So here also, like, if you cannot calculate by conventional means, you can use the right hand rule, but it's a little complicated than the others, but we can see. So the first thing it can do is that it can calculate, we can know what is the direction of the coordinate system. So I have drawn this two-dimensional coordinate system. So we all know the first quadrant is termed as 1, this is termed as second quadrant, this is third quadrant, this is fourth quadrant. So in the first quadrant, x-axis is positive and y-axis is positive. I mean, in the second quadrant, y-axis is positive, x-axis is negative. In the third quadrant, both are negative. In the fourth quadrant, y-axis is negative, x-axis is positive. That's what the convention says. So you can also see, like, if this is a point, in this direction, x is positive. In this direction, x is negative. In this direction, y is positive. In this direction, y is negative. So that's how, like, Cartesian coordinate system is designed. But this system is actually, this is two-dimensional, but you can have three dimensions as well. You can have another dimension as well. And that dimension you cannot present in paper, but basically this is x-axis, This is y-axis, and there's another dimension, third dimension, which is out of the plane of this paper or inside the plane. But I'm gonna write this because I cannot draw outside. So that's basically a third dimension of Cartesian coordinate system. So we want to know the direction. So for two-dimensional, the direction was pretty straightforward. I mean, its x-axis is positive this way, positive this way, negative this way, y positive this way, negative this way. But if it's a three-dimension, so then it gets a little complicated. So we can use right-hand rule to figure out what is the directions of the positive directions of the coordinate systems. So what we can do is that we can use our right hand and the index finger. So these fingers are gonna point towards the positive x-axis always. So this is the positive. So whenever you see a positive x-axis, you're gonna point your fingers toward positive x-axis, and then you're gonna curl the remaining fingers, and that's gonna point towards the positive y-axis. And then the thumb is gonna point towards the positive z-axis. So, I mean, in 2D it's easy, but in 3D you have like a space. So if your coordinate system is tilted in some way, so you can use your right hand to figure out what are the directions of positive x, positive y, positive z. We're not gonna use this system a lot, but that's the most accurate system to figure out the direction. For example, you have x-axis and then you have y-axis. So we know the direction of two coordinates, but we want to figure out what is the direction of the third coordinate. So we know that all of the coordinates are at 90-degree angle. So we know the z coordinate would be either outside the plane or it would be either inside the plane. So what we can do is like we can use right hand rule. So we know that we're gonna point our fingers towards the positive x-axis. So that's the positive x-axis. We're gonna point the fingers towards the positive y-axis. Then we're gonna curl the fingers, remaining three, or we can curl all four, but remaining three. So this is gonna point towards the positive y-axis. We know the positive y-axis is on the top, and so yeah, it makes sense. And then the thumb will point towards the positive z direction. So in this case, we can see my thumb is pointing outside the plane, outside this plane. So the direction of z is, if someone will ask you what is the direction of the z, you can use right hand rule and you can say that the direction of z is outside the plane. So if something is outside the plane, you put a dot and you put a circle. So in this case, if you put a dot and you put a circle, I will know, everyone will know that you know that the direction of the third coordinate system is outside the plane. So we can do another example just to clarify. So this is x-axis, this is y-axis. So if someone will ask you, so if it's out of the plane, you're gonna put dot and circle. If it's into the plane, you're gonna put cross and circle into the plane. So in this example, our fingers should point to the positive x-axis. So positive x-axis I've drawn this way. So I guess I'm gonna go do like this. So that's the direction of the positive x-axis. And then I'm gonna curl the finger and it's gonna point to the positive y-axis. So I guess everything seems okay. This is positive x-axis. This is positive y-axis. Now where my thumb is pointing? My thumb is pointing into the plane. So in this case, if I will ask you what is the direction of the z coordinate axis, you put a cross and you put a circle, that would indicate that you know that the direction, the third direction of z is inside. So that's how you use right hand rule to figure out the direction or the orientation of the coordinate system. There's another important thing right hand rule does, that is it can calculate, it can let you know the direction of the moment as well. So you know the counterclockwise moment was positive and the clockwise moment was negative in the statics class, and that's true here as well. But the right hand rule can let you know also the direction of the moment. So first step is to calculate the directions of the coordinate system, and if the direction of the moment and the direction of the coordinate system are same, then we will say the moment is positive, or anti-clockwise moment is positive, either way. So if the direction of the coordinate system is positive, but the direction of moment is on the opposite direction of the direction of the coordinate system, then it is a negative moment. I can give you some examples. So for example, in this case, or let's just draw one. So this is x-axis, this is y-axis, and this is a moment I have drawn. So what is the direction of z-axis? So this is x-axis, this is y-axis. The direction of z-axis is outside the plane. So I'm gonna put dot and circle, and I will say z is out of plane. Now we can calculate the direction of moment. So how we can calculate the direction of moment is that we're gonna curve our fingers wherever the moment is rotating, and then we're gonna see what is the direction of the thumb. So in this way, I can give two examples to be clear. So this is the moment, and this is one moment, right? So this one is counterclockwise, and this is clockwise. So in this case, we're going to curl wherever the moment is acting, and then the thumb will point the direction of the moment. So the direction of the moment is outside the plane. In this case, we're going to curl the finger this way because the moment is rotating this way. So our thumb is indicating into the plane. So that's the direction of the moment in this case. So in this case, it's out of the plane, right? This is the direction is out of the plane. So that's the moment which is being drawn here. So what is the direction of the moment? It is also out of the plane. So this is also out of the plane, this is also out of the plane. So they have the same direction. So I can safely say that this moment is positive. And you can also see it's anti-clockwise, so it's positive. So you can use anti-clockwise as well. But the most accurate one is the right-hand rule. So you can see how you can calculate the direction of the coordinate system. You can see how you can calculate the direction of the moments. I mean, you can calculate how is it positive or negative. But we also need to know, so there is a simpler way. The simpler way is, which we will use mostly. The simpler way is x is always positive this way, y is always positive upward, and z is going to be always positive out of the plane. So, I mean, if right-hand rule is difficult for you guys, then I guess you can use this one. So the x-axis is always going to be positive this way, y-axis is always going to be positive this way, z-axis is always going to be positive outside the plane. Similarly about the forces. Forces to the right is always going to be positive. Forces to the up is always going to be positive. Moment to the anti-clockwise moment is always going to be positive. So when I say 125 Newton force here, I say 125 Newton force here, when you guys will be doing the calculation, in the calculation you will use this because it's this way. So you will use negative sign to this. So this force is negative. So you will use, during the calculation, you will use a negative sign. But for these kind of forces, to the right, to the up, and anti-clockwise moment, these are positive. But that's what you were doing in like statics as well. And for the internal loads, it's a bit tricky, a bit different. So I can just let you know. And so this is axial force, this is shear force, this is moment. So axial force is positive when it's causing tension in the system. So what do I mean by that? So if it's a simply supported beam, you have a section cut and you're going to expose an axial force. This axial force is basically pulling this member, right? So it's causing tension. So if it's causing tension or pulling apart the member, it's positive. And shear force is positive when it's downward. And the bending moment is positive when it's causing, so for example, you have a bending moment, and this bending moment will cause bending. It's so what's going to happen, because it's a deformable body mechanics. Now you also will see deformation. So if you apply a bending moment, you're going to see bending something like this. You're going to see a bending. So if it's bending in a sagging way, then it's positive. But and we're going to do calculations, so it's going to be easy. So even if you don't understand now, it's fine. We're going to do calculations, and it's going to be super easy to understand the directions later on. But to simplify, if you are looking to a section on the left side, this force is positive if it's an internal force. This shear force is positive if it's downward, and this bending moment is positive if it's anti-clockwise. So that's the direction for the internal forces. So this is what we discussed. I mean, we talked about mechanics of material, we talked about branches of mechanics, we talked about some general principles, we talked about there are two systems of units, we talked about loading conditions, loading types, super important. We need to know external load, reaction load, internal loads, and then we talked about sign conventions. In the next lecture, we're gonna do some calculations. Basically, it's going to be revision of statics, and from the next chapter, we'll talk about stresses and strain. That's going to be chapter 2. Yeah. So thank you very much. Hope you enjoyed the lecture and have a good rest of the day.